Welcome to today's Explainer. We're diving into a topic that is absolutely crucial for any of us in medical facility engineering. We're going to thoroughly break down how to properly select a hospital UPS power system. We need to dismantle the dangerous illusions surrounding hospital UPS design and instead build what I like to call a verifiable safety chain. Because let's face it, the stakes here are astronomically high. We aren't just talking about losing a few files in a power outage. We are literally talking about direct threats to patient lives. Yet somehow, the way these systems are often sized is still riddled with outdated rules of thumb. So let's jump right in and fix this. We have to start by busting the absolute biggest myth in our industry. You know the one. The idea that choosing a hospital UPS is just a matter of walking into a room, adding up the wattage on the equipment nameplates, and throwing in a lazy 20% safety margin. Look, that's how you set up a battery backup for your home office, not a life-saving medical facility. The reality is much more intense. Proper UPS selection requires rigorous clinical risk assessments, extracting precise transient data from manufacturers, and complex system integration. It's a highly engineered ecosystem. Here is our blueprint for today. We'll be moving quickly through 6 key areas, taking you step by step from exposing that dangerous simple addition myth all the way to delivering a fully tested, compliant, and verifiable safety chain. Let's kick things off with Section 1, the simple addition myth, and why it's such a dangerous trap. Relying on a floor plan and looking at room names like ICU or surgery to size your power system, that's a recipe for disaster. Instead of just blindly adding up numbers, international standards actually demand this rigorous 7-step process. You've got to confirm local regulations, do a clinical risk assessment, dig up official manufacturer data, hunt down those hidden transient and peak loads, design your architecture, verify overall compatibility, and finally run rigorous tests. Remember, your power chain is quite literally only as strong as its weakest link. That brings us to Section 2, Standards and Risk Classification. You really can't talk about safety without understanding the strict rules of the game. And it's not just about how much power equipment needs, it's about the rules governing how that power is delivered. Check out the massive difference between these two global standards. The IEC standard categorizes spaces into groups 0, 1, and 2 based on the medical application, basically asking, are applied parts touching the patient, and will a power loss threaten their life? Meanwhile, the NFPA standard in the US focuses on categories 1 through 4, which define the broader risks to both patients and staff if the system fails. You absolutely must know which standard your region is actually enforcing. This guideline from the UK's NHS illustrates this perfectly. You cannot, and I mean cannot, mix up a room's risk classification with a specific piece of equipment's required interruption time. Just because an MRI is sitting in a Group 2 room doesn't automatically mean the whole machine needs a zero interruption UPS. Whether you need that sub-0.5-second rapid switching is entirely determined by the clinical risk of the procedure and the manufacturer's exact specs, not just the label on the door. All right, moving to Section 3, calculating the true load. So, if we can't assume interruption times based on room names, how do we actually calculate the load for complex medical imaging? Well, you have to play detective. You need to extract 4 exact data points from the manufacturer's site planning guide for every critical load. Steady-state continuous power is the easy one. That's what everyone looks at. But you also desperately need the peak power and its exact duration. You need the inrush and excitation currents, because those spike massively when the equipment turns on. And crucially, you need to know the regenerative energy limits. Let me give you a wild example that proves exactly why using generic kVA ranges is basically playing with fire. Take a CT scanner. Official planning guides from companies like GE Healthcare list average, RMS, and peak power separately for a very specific reason. When that massive, heavy CT gantry decelerates from spinning, it actually acts like a generator, throwing power backward into your electrical system. This regenerative energy can easily overwhelm and trip a blindly sized UPS. If you don't use the specific manufacturer's data, your system could literally crash the moment the scanner slows down. Which leads us perfectly into Section 4, resolving system compatibility. We've got the true load figured out, but even a perfectly sized UPS is completely useless if it clashes with the rest of your electrical ecosystem. Take a look at this table. It breaks down the distinct roles of your main power defenses. The UPS provides immediate power maintenance and cleans up power quality. The medical IT system, specifically the isolation transformers, provides insulation monitoring to protect patients from microshocks on a first ground fault. And your generators, that's your long-term heavy-duty backup. The key takeaway here is that they solve entirely different problems. They cannot replace each other, they have to work together in harmony. And getting them to work in harmony takes actual engineering. You can't just cross your fingers and assume a medical isolation transformer will play nicely with your UPS. When you energize that transformer, the magnetic core creates a massive inrush of current. If you use a generic formula to guess that inrush, you're asking for trouble. You have to verify the transformer's maximum peak inrush current against the specific fault-clearing capabilities of the UPS inverter. If you skip this, someone flips a breaker and you get a catastrophic system-wide trip. Let's move on to Section 5, batteries and backup generators. When the grid actually fails, this is your ultimate lifeline. When choosing your battery chemistry, you're usually weighing traditional VRLA, standard lead acid, against lithium-ion. You have to balance the lower initial cost of lead acid against the much smaller, lighter footprint of lithium. But honestly, the biggest deciding factor must be fire safety constraints. Lithium is incredibly popular right now, but it carries specific thermal runaway risks. You can't just pick it for its lifespan. You have to ensure your building's specific fire suppression systems and local fire codes actually allow it. Now, when it comes to pairing that UPS with the generator, look, there is this deeply ingrained, completely lazy rule in our industry that says you just size the generator at 1.5 times the UPS capacity. That is a myth probably older than the hospital itself. You cannot use a universal multiplier. You have to rigorously calculate harmonics, step loads, which is the chunk of load hitting the generator all at once, and the massive amount of power required to recharge depleted UPS batteries. If you don't calculate all of this, the generator's voltage is going to swing wildly, and the UPS will just flat out refuse to connect to it. Finally, Section 6, the verifiable safety chain. Up to this point, we've designed a really robust, highly calculated system on paper. But as we all know, paper doesn't save lives in a crisis. So how do you prove this system actually works under pressure? That is the million-dollar question. The standard requires you to rigorously validate this entire ecosystem through comprehensive factory and site testing. When the city grid goes dark, you cannot just trust the data sheets and hope for the best. A properly commissioned system has to survive a gauntlet of real-world tests. You have to simulate hard power outage, you've got to bring in massive dummy loads for full load bank testing, just to verify that the battery autonomy is actually as long as your math says it is. You have to test the sequential loading of the generator and ensure the medical IT fault alarms perfectly link back to the central monitoring system. Every single component must be pushed to its absolute limit, exactly as guidelines like the UK NHS mandate. Which brings us to our final thought for today's explainer. Take a hard look at the design of your own facility and ask yourself, is your UPS system a truly verifiable safety chain, or is it just a really expensive guessing game built on rules of thumb and assumptions? Ultimately, true engineering in healthcare leaves absolutely zero room for guesswork. It demands a fully verifiable safety chain to protect every single patient through every single crisis. Thanks for joining me on this explainer. Keep questioning the defaults, rely on the data, and I'll catch you next time.